Hey everyone, welcome. Today, we're going to tackle a classic coding challenge, how to reverse a singly linked list. Now, this is a really fundamental concept, but we're going to make it super clear by walking through it visually, step by step, all the way to the code. So let's dive right in.
So here's a cool way to think about it. A linked list is basically a one-way street for your data. Each car, or node, only knows about the car directly in front of it. So the big question is, how do you get all that traffic to flow in the complete opposite direction without causing a total mess? That's the puzzle we're solving today.
Okay, but before we can flip this thing around, we need to be absolutely crystal clear on what a linked list actually is. So let's do a quick breakdown of its structure. A linked list is kind of like a treasure hunt. See, unlike an array where all the elements are stored neatly side by side in memory, these nodes can be scattered all over the place. The only thing connecting them is that pointer, that little arrow, which tells each node where to find the next one in the chain. And that null at the end, that's just the signpost saying, hey, the road ends here.
All right, let's zoom in on the fundamental building block of our entire structure, the node. Each one is super simple. It has just two jobs. One, hold a piece of data, that's the value, and two, hold a pointer to the next node. And this is the absolute key takeaway here. It only knows what's next. It has zero clue what came before it.
Okay, so we've got a handle on this one-way street problem. Now let's get into the real challenge of reversing it.
Now, a super important point. We're not actually moving the nodes themselves. Nope, they're going to stay put right where they are in memory. The whole magic trick is just reversing the arrows, making each node point to the one that was previously behind it. So, how do we pull that off?
And this is what I call the oh no moment. It shows you the core problem perfectly. If we just grab our first node and tell it to point backward to null, well, we've successfully reversed that one link. But, look what just happened. We've completely broken the only connection we had to the rest of the list. It's just gone, floating out there in memory, and we have no way to get back to it.
Okay, so clearly that's not going to work. To avoid losing our entire list, we need a much smarter plan. And luckily, there is one. It's this beautiful, elegant solution that uses just 3 pointers. Let's meet the team. Here they are, prev, current, and next. Prev is going to keep track of where we just came from. Current is, well, the node we're currently working on. And next, this one is the hero of our story. Seriously, its whole job is to be our little bookmark. It holds our place for us before we break the link so we don't fall off the end.
Okay, theory is great, but let's actually see this in action. We're going to walk through the whole process and watch these 3 pointers do a little dance all the way down the list.
All right, here we go. This is our setup. Current kicks things off at the head of the list, which is node 1. And prev? Well, it's pointing to null because, there's nothing before the first node, right? Our next pointer is just waiting on the sidelines, ready for its big moment. Get ready for this 4-step dance. We're going to do this over and over for every single node. First, save our spot. Second, flip the pointer. And third and fourth, just scooch prev and current 1 step forward to do it all over again. Save, flip, move, move. That's the rhythm.
All right, let's do the first one nice and slow so you can really see what's happening. Step 1, we save node 2 in our next pointer so we don't lose it. Step 2, we reverse the link. Node 1's pointer now points back to prev, which was null. Boom, done. And finally, steps 3 and 4, we just slide prev up to where current was and move current to the node we saved. 1 down, 2 to go.
And now, we literally just do the exact same thing again. Save node 3. Reverse node 2's pointer to point back to node 1, then slide prev to node 2 and current up to node 3. See that? The chain of reversed pointers is starting to build up behind us. It's this awesome, predictable rhythm.
So we do that one last time, and then current hits null. That's our signal to stop the loop. And would you look at that? Our prev pointer is sitting right on what used to be the last node, which is now the new head of our fully reversed list. Perfect.
Okay, so seeing it happen visually is one thing, and honestly, it's the best way to get it to click. But now, let's connect that visual to the actual code you'd write in an interview.
And here it is. This piece of Python code does exactly what we just watched in that animation. You can see our 3 pointers right there, prev, current, and next node. And it's all wrapped in a simple while loop that just keeps running as long as our current pointer hasn't fallen off the end of the list.
Let's really connect the dots here, line by line. Next node equals current.next. That's us setting our bookmark. Then, current.next equals prev. This is the money shot. This is the line that actually reverses the pointer. And the last two lines? That's just us scooting prev and current forward to get ready for the next round. It is the exact same four-step dance we just saw.
So why is this such a classic interview question? Well, it's all about efficiency. The time complexity is O of n, which is just a fancy way of saying we only have to visit each node one time. We just walk down the list once. And the space complexity? O of 1, or constant space. That means we didn't have to create a whole new list, we did it all in place. Super, super efficient.
And that's really all there is to it. Once you've got this down, it really opens the door to a bunch of other, more complex list problems. So here's something to think about. If you can reverse the whole thing using this logic, how would you adapt it to reverse just a small section in the middle? That's a great next step to challenge yourself with.